Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
A quick free body diagram of the incline. We have angle theta here. We have some object here. Perpendicular to the surface of contact would always be the normal force. We have some angle here theta, and then going straight down would of course be the force due to gravity. And this is the direction of our initial velocity. We have new Cartesian axes, where here we have the y-axis and here we have the x-axis. And so we can then say that applying Newton's second law, mg sine of theta equals the negative be better to say negative mg sine theta equals ma, where here the negative x component, or rather the x component of the acceleration of the gravitational force vector is pointing downwards or down the incline. That's why we're denoting this as negative, and we're going to set this equal to the net force in the x direction. Let's cancel out the m's and say that the acceleration is equaling negative g sine of theta. So that'd be the acceleration in the x direction. And we can then say here, we can say that the final velocity equals the initial velocity plus the acceleration multiplied by time. We know that the final velocity at the top, it momentarily stops at its highest point, so this will be 0. And we find that t equaling negative v initial over a, this would be at max, rather, you could say highest point. Now, for part A, we can say that the position where the block stops, x, will be equaling velocity initial t plus 1/2 at squared. And this is going to give us simply velocity initial multiplied by negative velocity initial over a plus 1/2. My apologies. Plus 1/2 times the acceleration a multiplied by negative velocity initial over a quantity squared. And so x is simply going to equal negative velocity initial squared over 2a. So given this, we can find for part A, x equaling negative 1/2 multiplied by 3.50 meters per second quantity squared. This will be divided by negative 9.8 meters per second squared multiplied by sine of 32.0 degrees. Find that then x is equal to 0.18 meters. So this would be your answer for part A. For part B, the time it takes for the block to get there, t equaling velocity initial over a. This would be equaling to, my apologies, negative velocity initial over a equaling negative velocity initial over negative g sine of theta. And this is going to give us 3.50 meters per second divided by 9.8 meters per second squared multiplied by sine of 32.0 degrees. And this is giving us 0.674 seconds. So this would be your answer for part B. And then for part C, we have to recognize that the return speed is identical to the initial speed. And that's to be expected because there are no dissipated forces in this problem. There isn't any friction, essentially, in order to slow us down. So we can say that we're going to set delta x as 0. And we're going to set this equal to velocity initial t plus 1/2 at squared. And so for the total time up and down t, this would be equaling to negative 2v initial over a equaling negative 2v initial over negative g sine of theta. And so this is equaling 2 multiplied by 3.50 meters per second divided by 9.8 meters per second squared multiplied by sine of 32.0 degrees, and this is giving us 1.35 seconds. And here we can say that then the velocity when it returns is therefore equaling the initial velocity plus at. So this would be equaling to positive 3.50 meters per second. And then we're going to say minus 9.8 meters per second squared sine of 32.0 degrees multiplied by 1.35 seconds. And we should be getting velocity equaling negative 3.50 meters per second, which is equal to the negative initial velocity. And so we can confirm our answer for part C. That is the end of the solution. Thank you for watching.